In class we learned that the derivative of the logarithm function was 1 over x. Now if I use the chain rule, this allows us to calculate the derivative of the logarithm of any other function. So if I have some expression inside the logarithm, then the chain rule says you take the derivative of the outside function, which is the logarithm's derivative, 1 over the inside, 1 over u, and then you multiply by the derivative of the inside, du dx. Now, an interesting way to think about that is you take the derivative of what's inside and divide it by what's inside. So let's look at a couple examples to illustrate this principle. First, the derivative of the natural logarithm of negative x. So we identify what's the interior expression, u equals minus x. So the derivative of u prime, equals minus 1. Now I can take the derivative of the natural logarithm. The derivative of the natural logarithm of negative x by the chain rule is 1 over the inside, negative x, multiplied by the derivative, negative 1. And notice that the negatives cancel. So the derivative of the natural logarithm of negative x is 1 over x. And this is actually very important. The derivative of the natural logarithm of negative x and the derivative of the natural logarithm of x are both 1 over x. And we'll take advantage of that later in this presentation. Our second example is to look at the derivative of the natural logarithm of x to the sixth. So again, we look at our expression, and our interior expression is x to the sixth. The derivative of that expression is 6x to the fifth. And so by the chain rule, the derivative of the natural logarithm of x to the sixth is simply u prime over u, which is 6x to the fifth over x to the sixth. Notice that many of these powers of x are going to cancel, 5 of them, and I'm left with a value of 6 over x. Now this problem illustrates an interesting example as well. The properties of logarithms, the logarithm of x to the sixth can be written as 6 times the logarithm of x. And so if I take a derivative of the logarithm of x to the sixth, that's the same as the constant multiple 6 times the derivative of the natural logarithm. And that's just 1 over x. And so I get 6 times 1 over x. Notice that that's the same expression as what we just found. 6 over x and 6 over x. This suggests that maybe we should use that property of logarithms to begin with. The logarithm of the square root of x cubed, rewriting the powers, is really the logarithm of x to the 3 halves. And by the properties of logarithms, that's 3 halves times the natural logarithm of x. So when I take a derivative of the natural logarithm of the square root of x cubed, by the constant multiple rule I get 3 halves times the derivative of the logarithm, which is just 3 over 2x, or 3 halves times 1 over x. So this illustrates the principle that using the properties of logarithms, often we can find much simpler ways of dealing with derivatives involving powers. From the previous slide, we learned that the derivative of the logarithm of x equals 1 over x, and the derivative of the logarithm of negative x is also 1 over x. The thing that's different about these functions is their domain. The logarithm of x has a domain of positive numbers. In other words, my input has to be greater than 0. When I take the logarithm of negative x, this negative creates a reflection across the y-axis. And so the domain of this second problem is actually the negative numbers, where x has to be less than 0. Putting these two together, we can use the logarithm of the absolute value of x. Because the absolute value, when x is greater than 0, the absolute value replaces absolute value of x with x, but when x is less than 0, we replace the absolute value with negative x. When I now take a derivative for either x greater than 0 or x less than 0, both of those functions give the same derivative. And suddenly we have a new formula that is valid for all x, at least all x not equal 0. The chain rule still works, and so even if I include the absolute value of u, I still get the same formula for my derivative. Now, let's say I don't know the derivative of u with respect to x. If I can find the derivative of the left-hand side, and I cross-multiply by the u, this leads me to a strategy for finding du dx. We have a strategy for finding the derivative of u with respect to x when the logarithm of u can be simplified. And the strategy that we'll use follows the following 4 steps. First, simply identify the u that we want to calculate its derivative. Second, we'll write down the logarithm of the absolute value of u. Now this often involves products and powers and quotients. And we use the properties of logarithms. So those rules said we take the logarithm of a product. This becomes the logarithm of one factor plus the logarithm of the other. Similarly, the logarithm of a quotient becomes a difference. And finally, the logarithm of power, some expression to a power, becomes the power times the logarithm of the base. Now the advantage of these rules are, instead of taking derivatives of a product, we have a sum. And derivatives, the rule for a sum, are very nice. Similarly, for a quotient, the quotient rule is nasty, but it turns the problem into a simple derivative of a difference. And finally, we don't really have powers, or we don't really have a derivative rule for powers in general, and the logarithm turns that into a product, and the product rule is something we know. So we'll use those rules, and we can now differentiate the expanded version of the logarithm of the absolute value of u. And this takes care of computing the derivative of the natural logarithm of our formula. To find our actual derivative, we still need to multiply by u, and so this is the last step to recover the original formula. To illustrate these principles, I'll look at the following example. We want to take a derivative, and so here's where we identify our u. We want to take a derivative of x cubed times x squared minus 3 in the square root. Let's rewrite that as a power. X squared minus 3 to the 1/2 power. And we want to divide that by x to the 4th minus 1 to the 5th power. So that was step 1. Step 2 is to take the logarithm of the absolute value and expand using the rules of logarithms. Well, the logarithm of a product, the absolute value of a product is the product of absolute values. So we can replace this, each of the bases, we put in absolute values. Let's see. X squared minus 3. The squared only is defined for positive values, so let's just leave that alone. And x to the 4th minus 1 raised to the 5th power. So there's our logarithm. And the properties will allow us to take our logarithm of a quotient and turn it into a difference, and the logarithm of a product into the sum of logarithms. So I get the logarithm of the absolute value of x cubed plus the logarithm of x squared minus 3 to the half, and the quotient creates a difference. We subtract the logarithm of the absolute value of x to the 4th minus 1 to the 5th power. Now we can now use the property of logarithms with powers, and each of these powers can become multiples of a logarithm. 3 natural log of the absolute value of x plus 1/2 the natural logarithm of x squared minus 3 minus 5 times the natural logarithm of the absolute value of x to the 4th minus 1. And now I'm ready to use the rules of derivatives. So this is step 3. We'll compute the derivative of the natural log of the absolute value of u. We get the derivative of 3 natural log of x is 3 times 1 over x. The second term, we get a constant multiple of 1/2. And this time the logarithm has some formula inside, so it's u prime over u. It's 2x over x squared minus 3 minus 5 times, again we have a logarithm of a formula. We use the chain rule, x to the 4th minus 1, and the derivative of that is 4x cubed. So simplifying, we get 3 over x. The 2's cancel, so we get minus x over x squared minus 3, and that's plus, finally, minus 20x cubed over x to the 4th minus 1. This is the derivative of the natural log of u. And so step 4 says our final answer is the original formula. We get x cubed times the square root, let's leave it in powers, x squared minus 3 to the 1/2 over x to the 4th minus 1 to the 5th, and we'll multiply by that term we just found, 3 over x plus x over x squared minus 3 minus 20x cubed over x to the 4th minus 1. And that's my final answer.